Hello and welcome to episode 3 of Packet Tuesday. Well, we just made it here after Thanksgiving, so hope everybody's fresh and ready for more packets. We did have an episode last week, so don't miss that. No, with a lot of people taking off, maybe you didn't sort of follow up on your social media streams and such where we announced it. But yes, we did have an episode last week about DNS. But in this episode, I did want to step a little bit back down in our stack into the transport layer, into TCP. So no more DNS. Well, we'll probably come back to DNS at some point, but I want to talk about one feature that I find cause a lot of questions when we talk about this in Sec 503, and that's the urgent flag in TCP. The urgent flag is, well, interesting. It really sort of had one job and one job only. Remember, you connected to a remote system, the good old days with Telnet or now with SSH, and you are now sending, receiving a large log file, like you're doing like a cat on a log file, and well, all of a sudden you realize that this log file is a lot bigger than you expected it to be. So you want it to stop. And well, what you do is you do that Control C kind of, trying to get out of that cat command. And sometimes it works, but often it doesn't really work, doesn't really do anything when you're pressing Control C. And that's really the function that the urgent flag had, was to prioritize that Control C. Well, why does it not work? That's what we'll talk today about, what some of the problems are with that urgent flag and that feature. And with that, let's actually dive straight into the RFC, because that explains already what some of the problems are here. So let me just show you here the RFC. And in this RFC, well, you see here let me get rid of the little shiny part up here. So in this RFC, you do see the TCP header. We do start out with our source port here. We do have our destination port, our sequence numbers, our TCP header length, which is the offset at which the data starts. That's why this is called the data offset. Then we have some reserve bits, and then we have our flags. Now, what I have here is the original TCP RFC, and it's a bit small up here to see, so let me just write it out here. That's RFC 793. That's the RFC that I'm looking at here, and that's sort of the original TCP RFC. You see there are a couple flags you may have heard of, like ECN, that aren't defined yet. But we do already have our urgent flag defined. So here's our urgent flag. And with that, we got an urgent pointer. So how does this work? Remember, we're trying to prioritize that Control C. So the way this is supposed to work, let me just switch back here to just a simple whiteboard and clean this out. So we have our log file here that we sent, and that log file is split into different packets, and then we are sending the Control C here. At the time when we are sending the Control C, part of the log file has already been transmitted. So let's say this part was transmitted. So this is the sequence number we are at right now. Then the urgent pointer. So this is the sequence number that we are at when we are pressing the Control C. So the urgent pointer is basically offset here from the current sequence number to the prioritized data. So that's kind of how it is supposed to work, but there'll be a little bit issues, as you'll soon see. So the urgent pointer is basically how far do we have to go from the current sequence number to get to the urgent data. That's the idea. And the urgent pointer really only means something if the urgent flag is set. If the urgent flag is not set, then that pointer is ignored. And of course, the urgent pointer does not have to point to the current packet. It can point to a future packet. And you see here we have 16-bit for the urgent pointer. So with 16-bit here, this allows then for 65,535 as sort of our largest possible urgent pointer. So basically can point to data 64 kilobytes ahead of where we are currently at. So that's the basic idea. Now, okay, I do have the RFC open here. So let's dive into the RFC here a little bit more. And later here, it defines the urgent pointer. Here we have the urgent pointer. So this field communicates the current value of the urgent pointer as a positive offset from the sequence number in this segment. That's what I just told you. Yeah? So look at the sequence number, and then the urgent pointer tells you how far ahead you'll find the urgent data. The urgent pointer points to the sequence number of the octet following the urgent data. Okay. So basically what this means is that when I go back here to my packet and so my data, here are the different packets. Here's my current sequence number. Here is my control C, a couple packets on. So the urgent pointer would actually point to the byte after. So this is where the urgent pointer would point to, telling us, okay, everything, the part just before the urgent pointer is what you really want to prioritize. That's kind of what this means. Great. Well, let's actually dive a little bit deeper into the RFC. Okay, so here it says if the urgent flag is set, then send urgent pointer, that's SND UP, where send next -1 and set the urgent pointer to in the outgoing segment. So the urgent pointer is actually sent to the next -1. It's sent to the the actual urgent byte, not to the next one. So there's a little bit of ambiguity here. Is where do we send the urgent pointer actually to? The RFC here defines it sort of twice, and it's not consistent what it defines here. Well, we're not the first one to discover that, luckily or not so luckily. If you look at 10.11, and I already pulled this one up, it says, hey, page 17 is wrong. Page 17 is wrong. The urgent pointer points to the last octet of the urgent data. So not to the one after the urgent data, but to the actual last octet of the urgent data. So, okay. So not the first octet of the non-urgent data. Page 17 was the earlier one, and I don't want to go back up here, but where it said, okay, set it to the first byte of the non-urgent data. Okay. So, yeah, we got that cleared up now. Yeah. Well, sadly, this sort of keeps coming back here. And this is in 2011. Actually, someone created this RFC here. This RFC is 6093. And in this RFC, you can sort of, it's really sort of more a status report on what's going on here with the urgent data, and that there's basically incompatible definitions, and then here a little bit sort of how at the time, different operating systems implemented it. And more recently, see, this was just happened, August 2022. I'm recording this here, November 2022. We have a new RFC that actually obsoletes the old TCP RFC. And it now has sort of a little bit of a new chapter here on urgent data. So let's see where we have that. Yep, here it is. So what it says here, and that's again a little bit, so basically acknowledge here, as a result of implementation difference and middle box interactions, new applications should not employ the TCP urgent mechanism. However, TCP implementations must still include support for the urgent mechanism. So it basically says the TCP part should support it. The application part should ignore it. Okay. Yeah, and it gets a little bit more into the details here. But anyway, so much about the RFCs. So the RFCs are not really consistent here. And here in this very recent TCP RFC rewrite, they even sort of assume that, hey, the urgent flag was not really such a good idea, and that urgent pointer, maybe we should just forget about it and move on. Great. So let's see what really happens. After all, in Packet Tuesday, we want to get some packets going here. And what I have here, let me just clear out the screen, make sure that it actually worked. So here I have on the light green one here is a virtual machine that I'm going to use. And then I'm also going to collect packets. I'm going to collect packets here on the host of the virtual machine. Now, let me first show you what I'm going to do here. I'm going to use two TCP scripts to create connections with the urgent flag set and without the urgent flag set. If you're interested in these TCP scripts, they are, and actually should be able to just still pull that up here. Yeah, here is the URL for the Git repository, GitHub repository, so you can clone that yourself. This is something that Dave Holzer put together for SEC 503, and there's scripts from various instructors, and here also some scripts that I contributed with urgent flag and a couple other things here. But anyway, let's take a look at the script here. Okay, so this is our script here, and this is the normal script that we have here. I don't want to go into too much detail here, just show some of the highlights. I split up the payload into two packets. It's a simple HTTP request I'm going to send here. Now, at first, I'm going to do our standard SYN/ACK, our standard TCP handshake. And then I'm going to send these two payload packets. And I'm sort of trying, And I'm sort of trying to do the fin here in the end, but that's not really all that important. Okay, so let's see what happens. Let's create some packets here. And then again, before I do that, let me make sure that I am acquiring. Okay. Let me run this script. Okay, script is running. Looks like it works. Let's see what it looks like here. I'm using the capital A option here in TCP dump, which will display the payload or the packet in ASCII. It's a little bit similar to the capital X option, but without the hexadecimal part. It makes out of that HTTP part pretty nice and readable. Okay, and then it was port 80, and then the web server I used is at this IP address. And remember, I never like to set up filters when I capture packets because I can't go back and fix it if I mess it up. And sometimes I do typos. It's easier to filter once you're actually displaying the packets. But anyway, let's take a look here. Let's see what we got. Yeah, you see exactly. I had a typo here. Okay. As I told you, we have our get and then host www packettuesday.com. Okay. Now this went to port 80. Like most decent web servers these days, I'm going to just redirect you to the HTTPS version of this site. Great. You're seeing the 301 coming back. The one thing I want to point out is that the web server here echoes back the host name that I provided. Keep that in mind, because that'll tell us what did the web server actually receive. Because the web server will respond with whatever we send to it. And here I'm using as a web server Nginx. So I would say major normal web server. There's nothing fancy, nothing really special configured on that web server. Couple adjustments to headers and stuff like this. You see like content security policies and stuff like this, but nothing really that should affect anything that's happening sort of with TCP. Okay, so pretty much what we expected. We get the request being sent and a response comes back from the web server. The web server redirects us to the HTTPS version of the website. And the reason is interesting is because the web server echoes back the host name that we sent as it was received by the web server, and nothing really special here. That's what we expected. Great. So now let's do the same with the urgent flag set. So second script, the only difference in this script is that I set the urgent flag. Okay, we got it sent. Let's read it back. Okay, notice the urgent flag here. And then I set the urgent pointer to 30. Now, the first packet here is only 27 bytes. And so we have our get / HTTP 101 host www. So with 30, that should get us here like to the K, probably the C or the K here. That's where this points to, sort of a couple bytes into the next packet, because the first packet only had 27 bytes, and then so the urgent pointer of 30 was not in the first packet, it was in the second packet. Great. What was received by the web server? Notice how the K is missing here. We get paste secure Tuesday instead of packet Tuesday. We get sort of the missing K here. That's what happens. And that's sort of one of the problems that you run into with the urgent flag. Instead of prioritizing that byte actually gets lost. And that's why that Control-C doesn't do anything if you're using the urgent flag. You're better off not setting the urgent flag. And that's why the newer RFC tells applications, hey, don't use the urgent flag. Now, it says TCP implementations keep the urgent flag going because there may be some old stuff that still uses it, but really application layer, it doesn't do you any good. But that's odd, right? We would have expected, like reading the RFC, that hey, maybe the wrong byte gets prioritized, but everything should still get received. So why is this one packet, or this one byte really? It's not a packet, it's just one byte. Why is it being dropped? And for that, I want to refer to here actually to this book, Unix Network Programming. There's a standard API how Unix and really everybody is programming network connects. It's a socket API. A lot of the times, even if you're using languages like Python or such, they're really built around that socket API. And that's really sort of how it's implemented. And it talks here about the urgent pointer. Let me see if I can zoom in on this a little bit. Okay. So this is sort of the important part here. Let me just highlight this. So what happens? Basically, the problem is the byte that's being prioritized. We want to process it before we process the rest of the data. So this is what this OOB, this out of band mark, is connected to. And then it says, by default, the SO out of band inline socket option is not set for the socket. If that option is set, then it just leaves the urgent data alone, but by default, it's not set. So, okay, if this is not set, which is the default, then the single byte of data is not placed in the socket receive buffer. So the application will not receive that data. Instead, it puts it in a special place. There's sort of a separate 1 byte out of band buffer for the connection. But the application has to support that. There is a signal that's then being sent, and it's also talking about this here somewhat. Here the urgent signal that's being sent whenever the urgent flag is set, and the application has to listen for that signal and then grab that byte out of that 1 byte buffer. But if the application doesn't implement that signal, then, well, that byte is being lost because it's not being placed in the receive buffer. So the normal application processing never sees it. And this is what we have going on here, that it's not so much the ambiguity about where the urgent pointer points to, that's the problem here. It's really about whether or not the application bothered to actually implement this particular feature. Now, with that, let's take a quick look at how often do we actually have these urgent flags set. And I'm just collecting here to sort of the system I'm using here from my home network to capture packets. Not sure if you're familiar with this tool. It's called Archime. Used to be called Moloch. Some people still, my URL here still says Moloch. I haven't gotten around to change that yet. But Archime basically collects full packets and then stores summaries of the packets in Elasticsearch and makes them easy searchable. So we can quickly search here. What do we have? TCP flags urgent equals 1. Okay, looks like, now by default, it just looks at it for the last hour. Let's go back here a couple days. Back 7 days now. And see if we have anything. Yep. And here we got a couple of packets that we have here. Well, some of them are me playing here with Packet Tuesday. So that was me playing. And then I also got a couple here from some Chinese IP address. But these are just sort of single packets. So let's see what we got here. So these are not... These are not connections really. Okay, it's just a SYN packet was set, and the urgent flag was set. We can take a quick look at the IP address here and see, like, what else do we know about that IP address. We go to Internet Storm Center. You can always search for an IP address here. And yeah, it looks like we got quite a bit of traffic from that IP address, 600 something ports. And yeah, it looks like this particular IP address likes to set the urgent flag here. Actually, also the push flag. I'm not really sure what they try to accomplish with this. For the most part, it should be safe to just block packets with the urgent flag. I would say for the most part should. I'm careful with this because you never know what people are doing in the network. So definitely check in your network, if the urgent flag is being used. But it can definitely confuse the IDS because this is sort of one of those cases where you saw in TCP dump, we saw the entire packetuseday.com URL, but it was not actually used by the application. And whether or not that byte is being used depends on the application. And then it also sort of depends on the operating system, which byte is actually being placed in the urgent pointer, in the urgent buffer. So which byte may get lost. That's sort of where the ambiguity matters. Anyway, that's sort of what I had for today. Hope you enjoyed it. Hope you like what I'm doing here with these Packet Tuesday videos. And if you have any questions, let me know. Comments, please let me know. And tell your friends about it. Subscribe and like and do all the good stuff kind of that YouTubers always ask for. And I hope you just enjoy the packets. And I will create a pcap with just those two TCP sessions, the one with urgent flag, the one without urgent flag. That's the pcap that you'll then find as part of the collateral for this video. So thank you.